Yeah, welcome to my defense presentation. The topic of my presentation is fusing wireless communication with visual sensing, from sensor sharing to localization. Multimodal systems are ubiquitous in today's world. These systems adopt a group of multimodal sensors to collaboratively accomplish certain goals. For example, tracking and localization systems usually adopt vision sensors and wireless sensors to detect and track a subject's trajectory. Smart vehicle systems, such as vehicle-to-vehicle and vehicle-to-everything, require wireless communication between them to share vision or motion data. Another example is autonomous driving, in which a vehicle is equipped with multimodal sensors, including camera, LiDAR, radar, and onboard inertial sensors to achieve simultaneous localization and mapping. Although these multimodal systems serve in specific contexts and achieve different goals, there are several common challenges. The first challenge is sensor range. Different sensors have different sensing range and capability. How do we orchestrate these sensors to effectively enlarge a system's sensing scope? The second challenge is measurement quality. How do we combine measurements from different domains so that the final measurements is valid, is accurate, and high quality? And the third challenge is data association. The collected sensor data from different modalities sometimes share overlapping information or come from the same subject identity. How do we correctly determine the overlapping information and associate the data that belongs to the same identity? Yes? Oh, okay.
Hi, Hansi. I just
hi, Marco.
managed to switch laptops and join this meeting.
No worries. We're just started. This is the second slide, so you didn't really miss anything.
Great. Please continue.
Okay. These challenges are what was that? Okay, the challenges. So these challenges are not independent, but related to each other. Specifically, addressing the data association can also help to improve sensor range and data fusion. So let me further explain this by focusing on two sensing modalities, vision and wireless. They are very popular sensing modalities, and they exist in many multimodal systems. We're interested in them because they have complementary characteristics. So in terms of measurement quality and sensing range, while providing richer appearance information and more accurate spatial measurements using stereo or RGBD information, vision sensors, they usually suffer from limited range of perception, occlusion, or poor illumination. Wireless sensing, on the other hand, they suffer less from non-line of sight situations or appearance variations, but they're more prone to complex environments with multipath. So if we're able to fuse and associate vision and wireless data, it would allow each sensing modality to complement each other so that advantages are kept and drawbacks are canceled. In this thesis, I want to answer the following question. Can we efficiently incorporate wireless communication into visual sensing systems and improve their performance in terms of sensing range, tracking, and localization? To answer this question, we present novel approaches of sensor fusion and association for vision and wireless data. And I will focus on two contexts, and I'll discuss how data fusion and association would make benefits. The first context is under the topic of connected vehicle systems. Here, I will present Fusion Eye. This is a connected vehicle system that allows multiple vehicles to share perception data over vehicle-to-vehicle communication and collaboratively merge this data into a more complete scene. The second context is under the big family of tracking and localization. Here, I'll first present Wi-Fi, in which we associate visually detected persons with their smartphone identifiers using vision data and wireless measurements. And in the end, I will introduce Wi-Fi localization. Here, we want to produce camera domain spatial coordinates based on the user's wireless domain measurements or phone data. So let's start the first topic, the Fusion Eye. This is a perception sharing system for connected vehicles. A smart vehicle these days is equipped with various sensors to be aware of the surroundings. And although these sensors allow certain level of situation awareness, each individual's vehicle, the sensing range, each vehicle's sensing range is limited. And this can pose hazards on safety driving environments. And one way to prevent such hazards is to share what they see with each other. Recently, there are numbers of works that focus on sharing information for connected vehicles. The main goal is to share each participating vehicle's information with each other so that everyone has a better understanding of the surrounding. But the first category is DSRC or LTE-based sharing. Here, only the vehicle's own information is being shared. And the second category is sensor sharing. Not only each vehicle's own information, but also the surrounding information is being shared. In this work, we're more interested in camera sensing and sharing. So the basic idea of sharing and merging is as follows. Suppose the blue car can see a subset of the surrounding vehicles. And here we have a purple car that can see another subset of the vehicles. So if we share their perception, we can have a more complete scene of the surrounding. And let's use an animation to illustrate this process. So here, this is the blue car's perception, and this is the purple car's view. And now we share the purple car's perception with the blue car. So at the blue car's end, we need to fuse the shared data. It is important to identify whether a vehicle observed in both views are the same or not. In other words, we need to solve an association problem for these vehicles. So after correct association and merging, a global view is constructed and the field of view for each vehicle can be expanded. Our system has three major components: perception generation, perception sharing, and topology fusion. In perception generation, we first detect the vehicles for multiple views, and then we extract various kinds of features for these detected vehicles. Then in the perception sharing component, we share these features through wireless network to allow this information to be merged and fused at one end, which come to the third component, fusion. In this fusion component, we use a bipartite merging algorithm to associate vehicles from two views. So let's discuss the system in more detail. The first component is to create the perception, to create the view. We first conduct vehicle detection using YOLO, a pre-trained deep neural network, to obtain the detection bounding boxes. And we further assign a unique ID to these bounding boxes. Then we determine each vehicle's lane position by referring to the distance between the bounding box corner and the lane marker. We do this for the left car's view, and we do this for the right car's view. And then for each detection, we estimate each vehicle's longitudinal distance. So assume that the world coordinate is coincident with the camera coordinate. Using camera projection geometry, we would need the lateral coordinates in pixel, as well as the lateral position in the real world coordinate to estimate a vehicle's depth using a mono camera. And we assume that the observing vehicle and the detected vehicle is driving on the highway in a lane-keeping fashion. So the lateral distance between them can be approximately the same as the lane width. And using this approximation, we're able to estimate each detected vehicle's depth. So using the vehicle's depth, lane level position, we can construct individual local dynamic map for each observing vehicle. As shown in this plot, we do this for the left car, and then we create local dynamic map for the right car. And we can abstract it into topologies. Here, the rectangles, the triangles represents ego vehicles, and the circles represent the detected vehicles. And the y-axis represents the depth with respect to the observing vehicle. So after individual topologies are constructed, we use bipartite graphs to associate two views. In a bipartite graph, each node represents a detected vehicle. An edge score describes two observed vehicles' similarity. The less the score is, the more similar they are. Under this mindset, we propose several ways to compute edge scores. First, spatial score. We convert two vehicles' depth to the same coordinate and compute their differences. The smaller the score is, the more likely that the two cars are at the same place. And that says that the two car might be the same one. And another one is color score. We extract color histogram for each vehicle using 24 bins, and we compute Euclidean distance between two normalized color histogram vector. Furthermore, we can have some advanced score like key point. We compute the average difference for all the key point matches from the two detected vehicles. Here we adopt sift and serve to be the two methods that calculate distinctive features from images. In the bipartite merging algorithm, we use one or two or different combinations of these scores. The fully connected bipartite graph on the right, it contains all the potential association pairs for all the detected vehicles in two views. So we can see there are 3 on the left, 2 on the right. So in all, there can be 6 potential associations. And here we use the Hungarian algorithm to obtain an optimal matching that has a minimum sum of scores. So we will use this matching as the final association. In our implementation, we define 2 types of packet format for transmission, light-weighted and heavy-weighted. The first type of packet contains depth and color histogram information. So depth is just a floating point number, and color histogram is a 24×1 floating point vector. So they're small in size, but they're very essential to solving the association between two views because they're the fundamental information we need. So we send them twice during each transmission when we collect the data. And the second type of the packet contains more advanced features like sift and serve. So because they're large in size, we split the descriptors into batches so that each batch is within the buffer size limit. Each batch contains 1 sift point or 2 serve point along with the batch ID. And because they're large in size and not that important as the location and color information, we only transmit them once in the experiment. And in our experiments, 2 observing vehicles were driving side by side at the normal speed on the highway, and each equipped with GPS module, a camera, just a normal camera, and a wireless router that runs on 802.11ac. And the camera is recording each vehicle's front view, while the information is being shared between the 2 routers through 2 laptops. And we use NTP for time synchronization. In total, we collect 2 hours of video with around 2,800 pairs of valid frames, and overall 3.3 gigs of information being exchanged over Wi-Fi. So the left figure here presents precision, recall, and F-scores for 4 association policies in which different combinations of features are used to compute the edge scores in the bipartite graph. As we can see, only using depth information already gives us 84% accuracy, while the best accuracy comes with the combination of when we transmit depth, color histogram, and serve descriptors. This gives us 88% accuracy in F-score. So we notice in general, the performance of the merging algorithm improves as we use more fine-grained descriptors to compute edge scores. But this improvement in terms of accuracy is only marginal. We're also interested in how much information is shared to achieve this level of accuracy. So the right figure presents the average transmitted data size per video frame when we collect the data. We can see that the first 2 configurations consume much less bandwidth. They're around hundreds of bytes, while the served and sift features, when they're transmitted, they consume significantly more bandwidth, in average more than 10 kilobytes. So the analysis here gives us an insight that maybe serve and sift features does not provide a big win in terms of accuracy and bandwidth trade-off, because they consume so much bandwidth, yet brings just a little bit performance gain in terms of association precision. So after looking at this trade-off, let's come back and focus on the bipartite matching and its limitation. We know the the Hungarian algorithm will always try to find a match that has the minimum sum of edge scores. So the bipartite algorithm may give us false positive matches, especially when there are no overlaps between 2 views. So it is necessary to further explore better feature representations and further prune the bipartite graph to filter out those false positives. So inspired by the approaches used in face verification, we propose a Siamese network architecture that learns representative features for every image. The architecture contains two branches that takes in a pair of images. Both images go through the same deep network, and the network serves as a feature extractor. Here we modified the ResNet 18 by getting rid of some of the deeper layers. And the output feature FU and FV, they're 128 by 1 dimensional. They, along with the ground truth, they will be fed into the contrastive loss function. The intuition behind the contrastive loss is that we want feature vectors of the same identity to be close, and those of different identities to be far apart in the high-dimensional space. Okay, and the architecture we introduced just now essentially learns feature representations from appearance information. And with some adjustment, we can further incorporating spatial and kinematic information during the training process. So recall the spatial score we just defined when we introduced the edge score choices for the bipartite graph. We can split this spatial score into two parts and append them to the output feature of the network, while still remaining a property that their distance represents similarity, right? And then we add a fully connected layer that converts the 129-dimensional vector into a final 64-dimensional output vector. So through the training process, the fully connected layer essentially learns how much weight it should put on the appearance information and the spatial information, respectively. So here we present a ROC curve to compare the representativeness of different features. We predict whether two vehicles belong to the same one based on the Euclidean distance of their feature vectors. If the distance is smaller than the threshold, we predict that they're the same. Otherwise, we predict they're not. So each feature representation provides a different binary classification model. And this plot essentially shows the performance of different binary classification models at all thresholds. As we can see, the deep learning features learned from appearance and kinematic information shows the best performance. It has the largest area under curve, 93%. And furthermore, we can bring the feature vectors into the paradigm of bipartite matching. The bipartite edge score now become the Euclidean distance of these feature vectors, these deep learning feature vectors. So we first compute a maximal matching using Hungarian algorithm, and then we filter out potential false positives based on the pairwise re-identification. So as this table on the right shows, we can further improve the association precision from previously 88% to 96% by using the deep learning features into the bipartite matching algorithm. In terms of bandwidth requirement, deep learning features also show competitive performance. Recall that SIFT and SURF features use multiple key points to represent one image. And one key point is either a 128 or 64-dimensional floating point vector. Our deep learning feature vector, on the other hand, represents the whole image using a 128 or 64 floating point numbers. So the transmitted data when we use deep learning feature will be much less compared to the situations where we use SIFT or SURF. It is about 1 order of magnitude less. So to conclude the first part of the thesis, we explored the design space of a V2V perception sharing system. Specifically, the bipartite matching framework adapts well to different combinations of features, and it provides us an opportunity to explore the accuracy and bandwidth trade-off. And our result shows that the deep learning features here are more preferable from a bandwidth accuracy trade-off perspective, because it shows the best association accuracy at a medium bandwidth requirement compared to other configurations. So far, we have seen a system that shares vision data so that sensing range of each node can be expanded with the help of Wi-Fi communication. However, in this system, wireless data is just a medium. It serves no other purpose but bringing vision data from one end to the other. Next, we want to give wireless data a little bit more purpose by making it a separate sensing modality. So the second topic is focusing on associating vision data and wireless data. Let's consider the following context. A group of pedestrians are walking through an area where a facility camera is monitoring. Some of the pedestrians' smartphone devices are connected to a nearby access point. This is common in daily life. It can be a shopping mall, it can be a warehouse, or an outdoor smart intersection where we have camera and Wi-Fi access point equipped on the nearby roadside unit. In these scenarios, the camera is able to detect a subset of the pedestrians. And at the same time, the Wi-Fi access point can receive different wireless messages from the smartphones. However, here we don't know which person sends the specific wireless message. And our goal is to associate each visually detected persons with their smartphone devices. There are many benefits of this association. It could improve tracking and localization. It could also provide a means to send messages to devices observed on camera. Previously, related work that tackled this association problem would extract features from vision and wireless modalities that are comparable. From the camera modality, bounding box detection or silhouette images are processed to extract persons' location and their moving patterns. From the wireless modality, received signal strength, channel state information, or IMU measurements are analyzed to decode a pedestrian's spatial information. And the association can be achieved by comparing the similarity of the extracted features or solving a global optimization problem for all the multimodal measurements. Some of these works, however, extract pedestrians' appearance information for fingerprinting, and they will suffer from appearance variation, of course. Other works that formulate this association task as optimization problems, they rely on long sequences of measurement and cannot run in real time. And furthermore, many of these works focus on constrained or controlled environment where the user participants always appear in the camera field of view and there is no other passersby. So our method, we explored the measurements from both modalities and try to find a linkage that helps to associate one domain with the other. So from the camera modality, we collect detected pedestrians' bounding boxes and depth information. Over time, this information reveals a pedestrian's trajectory with respect to the camera coordinate. In the wireless domain, we collect the smartphone's IMU data and Wi-Fi fine timing measurement. Here, Wi-Fi fine timing measurement is a wireless protocol included in 802.11 in the year of 2016. It measures the relative distance between the smartphone and the Wi-Fi access point. So likewise, a sequence of IMU and FTM could also provide a pedestrian's trajectory information, but this trajectory is with respect to another reference system. Here, we don't assume that we have the precise location of the camera and wireless access point, so we cannot perform coordinate transformation directly and compare the shape of the trajectories. But intuitively, the trajectory information for the same identity should still be similar in some high-dimensional space, and we need to find effective representations for them. So here we propose a deep learning architecture that learns representative features from sequential multimodal measurements and determine their similarity by predicting an affinity matrix for all the bounding boxes and all the smartphone candidates. And as a baseline, we use, again, the bipartite matching algorithm to determine the association between them. We extract motion features, including trajectory shape, heading angle, and the relative distance from sequential measurements, and use these features to compute edge score for the bipartite graph. In this example frame, we have 7 detections. 3 of them are carrying smartphones, and the smartphones are exchanging messages with the access point. the affinity matrix on the right shows the ground truth association between the detected bounding boxes and smartphone devices. The cell at the ith row and jth column represents whether the ith device is associated to the jth detection. In this example, the bounding box number 2 is associated with smartphone A, and bounding box number 1 is associated with smartphone B, and bounding box number 7 is for phone C. Here we use an extra row and extra column to include situations where none of the camera detection is associated to a phone or the other way around. So this allows us to handle passersby users where that they don't have a phone that's communicating with the access point, but they appear in the camera field of view and there is a bounding box for them. So to train the network, we input pedestrian's camera modality measurements and smartphone wireless measurements within a time window for everyone. And the input in each branch go through an LSTM unit so that the sequential data will be rendered into feature vectors. And then we enumerate all their concatenations and combine these feature vectors into a feature ensemble. And then we use several layers of fully convolutional layers to reduce the dimension, or squash this feature ensemble cubic into a two-dimensional matrix. And now we further append extra row and extra column to this matrix, and then compute losses based on the ground truth affinity matrix. So in this way, the network is trained to directly predict an affinity matrix. And this affinity matrix, every cell of it represents the association probability between a specific bounding box and a specific smartphone device. In terms of data set, we collected our own large-scale data set to train and evaluate our network. In total, there are 94 video sequences across 6 different indoor and outdoor scenarios. All the participants are walking in an unconstrained fashion. They are free to walk around at their comfortable speed, and they may frequently exit or re-enter the camera field of view. When we tested the network, we have 2 ways of predicting the associations. The left figure shows how mode 1 inference is proceeded. Each rectangle bar represents the duration of a bounding box or a tracklet in the video, in the test video. Notice that the same user might have different bounding box IDs, because when they exit the field of view and then come back, the tracker would assign a new ID to them. And different bounding boxes appear and disappear asynchronously. So here, for clarity, we use a cursor to indicate an inference at a timestamp, and we use the information from the available available bounding boxes along with their recent measurements within a history window, and all these available wireless measurements to predict the association for the current frame. Here we choose the window size frame to be 10 frames. And in our implementation, the video is sampled at 3 frames per second. So here we're predicting the current frame's association based on a 3-second history. This is nice because it can work in real time if we maintain a buffer that holds the most recent 3 seconds information, and that's totally feasible. The second kind of inference is an upgrade on this on the mode 1 association. We introduce a voting scheme by keeping a record of the past association decisions. So for every new association decision we made in the online stage, for every frame, we can update the final association assignment using the majority prediction in the voting history window. And this intuition is that the consecutive association assignment between consecutive frames should be correlated and consistent. And this voting scheme allows us to further improve association accuracy. The metric we adopt to evaluate association accuracy is identification precision. It computes the ratio of the number of correctly associated bounding boxes over the total number of bounding boxes. We present results for both indoor and outdoor scenarios. We also conduct ablation study by changing the measurements of the wireless modality and see how it affects the accuracy. Overall, we see the combination of fine timing measurements, FTM, and IMU inertial data leads to the best accuracy. We have 80% and 81% accuracy when we do not adopt the voting scheme that's running more offline style. If we use the voting scheme, the accuracy is further improved to 87% and 91% respectively. So to wrap up this work, we address the problem associating moving subjects across vision and wireless sensors using camera bounding box coordinates, depth information, Wi-Fi FTM, and IMU measurements. More specifically, we design a deep network that leverages multimodal input to directly predict an affinity matrix that represents the association decision for every pair of bounding box and smartphone device. Our results show that the network is robust to complex situations where passersby exist and user participants can exit and re-enter the view. Before we move on, let's review the first two parts and see how they fit into the big picture. In the first part, we talked about sharing vision data using wireless as a medium. In the second part, we just talked about we incorporated wireless sensing into visual sensing, not for the purpose of communication or sending messages, but to provide data measurements from another modality. And we pointed out that association is one of the fundamental tasks. We provided a solution in the context of pedestrian tracking. Next, I would like to further exploit wireless and vision modalities. What can we do besides assigning correct Wi-Fi identifiers to vision detection? Can we assign something to wireless data the other way around? Or can we draw some useful information from the wireless data so that they can be understood by the vision side? So this is where the third part of the talk fits in. I'd like to introduce Wi-Fi localization. The goal is to predict or produce or generate a camera domain spatial information, a coordinate, simply based on users' phone data, users' wireless measurements. For example, we hope to produce a 3D coordinate with respect to the camera based on a user's wireless data. To better motivate this project, let's revisit the roadside unit and pedestrian scenario. Suppose there are only two pedestrians. Bob here is detected by the camera. Alice, for some reason, is not. So the roadside unit has only one piece of vision data. At the same time, both Alice and Bob's smartphones are communicating. They're in the coverage. They're communicating with the access point. And so the roadside unit receives two pieces of wireless messages. Now we want to determine the positions of these Wi-Fi message senders, both Bob and Alice. In other words, upon receiving a wireless message, can we know where the sender is? Where is he or she with respect to the camera? And so this cross-modal localization has many usage. First of all, accurate location and coordinates is always very important to pedestrian safety. And moreover, by providing a location estimation, we can compensate the situations where pedestrians are not detected by the camera and not see on the camera side, like the situations for Alice. There's a lot of related work on localization itself. As we discussed, localization can be achieved by vision and wireless alone. Vision localization uses RGBD information or point cloud with detection to represent a detected person's location. Wireless localization, there's even more. There's GPS positioning, IMU dead reckoning, Wi-Fi fingerprinting, and ranging trilateration. And when they're combined, the related work in the cross field includes filter-based approach, like Kalman filter or particle filter, where different sources of measurement and observations helps to reduce the localization error. And there is SLAM, in which a mobile agent relies on vision and wireless data to locate itself, and at the same time creating a representation of the surrounding. However, these works, they all assume the data association is known. And they all assume that data from both modalities are available all the time. But if any modality is unavailable, then this typical filter-based approach or SLAM approach, they would become inapplicable and infeasible. So this limitation poses a challenge in our context because we have one person's visual data and two persons' wireless data. So how do we fuse them to obtain location estimations for both of them? And here we don't know the association between vision and wireless data. So it's impossible to simply aggregate two observations from two modalities or taking their average. Even though we solved the association in the previous part, we would still have difficulty fusing a person's multimodal data if we only have his wireless data. In this example, we might be able to fuse Bob's vision data and Bob's wireless data after correct association. But we cannot do the same for Alice because she is out of the field of view. We don't have her camera data. So her location estimation can only be derived from wireless data. And the location estimated in this way is usually less accurate because only one modality's information is taken into account. So Alice might say, that's not fair. Bob can have a better fused location estimation just because he is detected by the camera and I am not detected. But I am also in the vicinity and my smartphone is also opted into the service. I'm also communicating with the roadside unit. I want to have the same localization accuracy as Bob. So can we make Alice feel better? Can we estimate or improve her location using her phone data and other people's vision data? And the answer is yes. To see how we develop our solution, let's start with one person. In this case, association for Bob alone is trivial because there's only one person. We can view the fused location as the output of a mapping function that takes both modalities measurement as input. And this mapping function can be also viewed as the process of correcting the GPS error using IMU, FTM, and camera data. And we know because GPS measurement is affected by the satellite's constellation. So the GPS error for different pedestrians within a certain range, within the same area, they're usually correlated. So this mapping function for Bob is also applicable for other pedestrians. So next time when Alice comes close, even if she is not detected by the camera and we can only have access to her smartphone data through wireless, we can apply the same mapping to her smartphone data. And this allows us to produce a location to let us know where she is with respect to the camera. So based on this intuition, we propose a generative adversarial network architecture to generate camera coordinates from phone data, from wireless data. For a pedestrian, a sequence of his vision data and a sequence of wireless data are rendered by two LSTM units into feature vectors. And because these feature vectors, they represent the same pedestrian. So here we use the embedding laws to force them to be close to each other in the high dimensional space. And this ensures the linkage between the two modalities. And then the wireless feature vector goes through a generator that produces the predicted coordinates as X, Y, and Z. And the predicted coordinate is then examined by the discriminator, and we use the GAN laws to train the generator and the discriminator. This involves a two-step min-max optimization. The goal of generator is to create or produce some valid good coordinates that is within the distribution of the pedestrian's true location. And it tries to pass the examination of the discriminator, while the discriminator will stringently discriminate the examine the coordinate generator produced, and it will penalize if it believes that the coordinate is a fake one. Here we also add a regularization term that it penalizes the reconstruction loss of the predicted coordinates and the true coordinates. So in this way, both generator and discriminator will become better and better. Eventually, an equilibrium will be achieved where the generator can generate very convincing coordinates. In other words, the coordinates are accurate or as accurate as possible in terms of the generator. And also it passes because the discriminator is also stronger. So the quality of the generated coordinates is good. And notice that when training the network, we need data from camera domain and the smartphone domain. But when we test the network, when it's in inference, we only need a person's smartphone data, as the yellow shaded area here shows. In terms of the data, we reuse the outdoor data from the Wi-Fi dataset. Here we have 79 sequences video sequences, and each video sequence is 3 minutes. It covers 5 outdoor scenes, and there are 3 user participants holding a phone, and there's phone and camera data correspondence is recorded. And in terms of baseline, we compare our methods, our network produced location with the phone's original GPS reading. It's just that the phone's original GPS chipsets. And we compare it also with a particle filter approach that fuses the GPS with the FTM ranging. So our first evaluation focuses on all users across all scenes. We train the network with all users' data in 74 video sequences across 5 scenes, and we test the network on the 5 test sequences, each in a different scene. These box plots compare the localization error of different methods at different scenes. And we see that our method consistently produces more accurate location estimations. When looking at the mean value, our method has only 1 to 2 meter localization error. In contrast, the phone's original GPS and the baseline, the particle filter baseline, have much higher localization error. The original GPS, the localization error varies from 3 meters to 16 meters at scene 5. At scene 5, there are 2 tall buildings besides us. So when we walk around, the GPS is really noisy, and we observe that the pedestrians' location are at the other side of the street. So that's why the GPS error is very, very high. And for the particle filter approach, we do see some improvement in localization error, but it's not as significant as our GAN-produced coordinates. The particle filter approach has the localization error range, in average, ranges from 2 meters to 10 meters. Besides box plot, here is a more detailed table showing everything. It shows localization error in average, standard deviation, median, and the 95 percentile. Overall, in average, when we compute the error across all 5 scenes, we see that the original GPS has a localization error of 7.4 meters, and the particle filter approach has a localization error of 5.3 meters. And in contrast, our method only has 1.554 meters, which is significantly lower. So we have seen that the network can produce more accurate locations for users and scenes that it had seen in the training set. Now, it's natural to ask whether the network can work for unseen participants or unseen environments that are not in the training set. So here, to do that, we train the network using only 2 persons' data, and then we test the network using the 3rd person's data that's not seen in the training set. And from these 3 figures, we see again that our method produces better location estimations than baseline approach. This result suggests that the network can be used to generate accurate locations for other unseen pedestrians at the same place. And this is consistent with our previous argument that the GPS error for multiple pedestrians is correlated, so that the learned GPS correction mapping can be applied to others, even it is not trained with that person's data. And we're pleased to see these results because in reality, there are so many pedestrians walking around the intersection every day, and it is impossible to collect multimodal data for every one of them. But our network does not require to be trained on everyone's data. We can just train the network using a reasonable amount of data from a group of pedestrians and let it do the work for the others. Again, here's a table that contains more detailed statistics. Readers can refer to it if they're interested in these numbers. So next, we want to see if the network can be generalized to other unseen environments. Here, we train the network using all users' data across 4 scenes, and then we test the network using the data from the same group of users on the 5th location that's not seen in the training set. Here, unlike unseen participants results, this time we cannot draw the conclusion that the network produces good location estimations at a place it has never seen before, as the localization error here of our method is no longer significantly less than the original GPS readings. Instead, for most cases, they're about the same magnitude. Only one exception is at scene 5. But we say this is because the original GPS itself is so bad. Even we have a significant improvement in terms of GPS localization, we still cannot say that our method can always work at a place that it hasn't seen. But we're not surprised by these results because we are aware that the network trained at one place can only correct the GPS error at that place. When we change the environment, the satellite constellation changes, and so the GPS error model changes. So unless the network is trained using the data at that specific environment, we cannot expect the network trained at one place to produce equally good location estimations for pedestrians at a different environment without any fine-tuning. So here we provide a corresponding table that contains all the critical numbers. Again, readers can take a closer look if they want to make a more quantitative comparison. So the evaluations so far have told us that the network is able to make good location estimations for unseen participants, but not at unseen locations. If we want to deploy the network at a different scene, we will have to train the network with new scenes data. However, data collection and labeling these correspondences are exhausting. And coming up with a semi-supervised or unsupervised approach is the key for the network to work at larger scale. Here, we introduce a self-learning approach, and we will see how the success of unseen participants and the self-learning in combination, it makes feasible for the network to work at unseen locations. So suppose the network is just deployed at a new place, and we only have very limited data sets to initially train the network. To obtain such limited data sets in an easier way, we could either hire one user participant with special clothing to walk around the scene and collect that person's data automatically using object detection and record camera and phone data. Or we can just let the roadside unit record everything for everyone, but we only choose to collect the data when there are only a few pedestrians around, and determining their camera phone correspondence is trivial and can be automated. So after that, during inference, the network can produce its coordinate from a pedestrian's phone data. The produced coordinate is reasonable, but not the best location estimations. So from the roadside unit, we can also fetch the camera data like bounding box coordinates. And this gives us a chance to do association, because each GAN produced coordinate is mapped to a piece of phone data. So associating the GAN produced coordinates with the existing bounding box coordinates essentially provides us with additional camera phone data correspondences. And this association is not complicated. We just compare coordinates relative distance. We choose the closest bounding box coordinates as a GAN-produced coordinates association pair. And then we can combine the initial data set with the additional data to form an extended data set. As time goes by, this feedback loop actually accumulates the data set on its own, and we can do more training using the expanded data set, and we can further improve the network's performance. So to evaluate self-learning, we compare the localization error of 3 different configurations. Here, the test set still contains 5 video sequences taken at 5 different scenes. Here, they're all treated as unseen environments. And the first configuration is without self-learning at all. They're the first column of these box plots. This is similar to the previous evaluation on unseen locations. We train the network using 4 locations data and then test on the 5th location. We do this 5 times for 5 different scenes, and we plot the overall localization error. The second configuration is with self-learning, and we just use the initial training. Here we use 1 person's data to initially train the network. Because we have 3 user participants, we can choose A, we can choose B's data, we can choose C's data to train the network. We choose different persons' data as the initial data set and show the localization error during the test phase. And the last configuration is self-learning after initial training and then association when the data is expanded. So we use the initially trained data to make inference for other pedestrians. And then we gather those data. We gather the association pairs to automatically accumulate additional data sets. And then we train the network again using the expanded data. And then we compute the localization error on the same test set. So from these results, we see that the self-learning can further improve the localization accuracy. In a practical perspective, when we deploy the network at a new place, we can first train the network using the limited data set, and then use the self-learning approach to automatically accumulate more additional data and further reduce the localization error through more training and fine-tuning. So here we also summarize the average localization error in this table. It's worth mentioning that the drop in localization error does not necessarily come from perfect association. Here we compute the correctness of the association and find out that the precision is just 70 to 80%. This means that there are false positive matches in the auto-generated dataset, but our self-learning is tolerable to these wrong associations. One reason is that most of the association is correct, so the data from true association plays a more significant role in the training phase. Another reason is that for those incorrectly associated camera bounding boxes, their coordinates are not too far away from the true locations. So they don't significantly degrade the error correction model that the network is learning. And additionally, we compute the localization accuracy gain, and we observe that it can improve the localization accuracy up to 26%. To wrap up this work, we propose a GAN architecture that produces accurate camera coordinates based on a user's phone data. The network only needs phone data during inference, so there is no dependency on data association, and it works for the unseen participants in the scene. Furthermore, we propose a self-learning approach. It uses the network's own output to do association and let us obtain additional camera phone data correspondences without manual data collection or labeling. In the end, let's come back to the 3 challenges that we mentioned at the beginning. To address these challenges, we first propose Fusion Eye, which uses wireless communication to share vision data across vehicle so that each vehicle's field of view is expanded. And then we move on to Wi-Fi, where wireless not only serves as a medium, but also plays a significant role in the task of associating visually detected pedestrians with their smartphone devices. And finally, we talk about a novel sensor fusion approach, deep learning, which a pedestrian's visual location can be estimated from his phone data. So there are several branches of future work that's worth exploring. For example, in the in the V2V system, more complex and more crowded traffic environment could be evaluated, and other traffic participants like human, like pedestrians or cyclists, can also be taken into account. And in the context of the roadside unit and pedestrian situation, we need to be aware of the potential privacy concern, as users' smartphones are actively communicating with the access point, and it's transmitting motion data. So how to protect users' privacy under this camera access point configuration is definitely another interesting research direction. Here is an acknowledgement of my previous publication. Readers can find more details of this presentation in these pieces of work. That's all for my presentation today. I'd like to thank all the audiences for attending my talk. And I want to especially thank my committee members. Thank you, Dr. Ray. Thank you, Dr. Yingying. Thank you, Dr. Hongsheng, for your interest in my work, for the continued support and all the valuable comments. And here I'd like to express my sincere gratitude to Marco and Kristin. Kristin was the instructor of my very first course at Rutgers, and her lucid and elegant lecturing kindled my passion for computer vision. And during the time I worked on my master technical paper, she was my mentor and gave me precious guidance on literature surveying and academic writing. And the training I received from her prepared me well for the upcoming PhD adventure, where I met Marco. And Marco walked me through the PhD journey step by step. He shaped me into an independent and self-motivated researcher. He taught me how to identify problems, how to analyze problems, how to conduct experiments, how to evaluate results and data, and how to express and articulate my ideas in the form of papers and presentations. As a role model himself, Marco showed me determination and perseverance when confronting challenges. And as a friend, he would invite us to his home for Thanksgiving dinner so that I don't feel homesick or lonely as a foreign student studying abroad. I wish I had the time to express my gratitude to all those who helped me during my PhD study. They're amazing administrative staffs, Christine, Noreen, Elaine, and Lisa. They keep everything so organized and make WinLab a wonderful place. And I will also remember the time I spent with my cohorts and colleagues, and the fun moments we shared make my life more colorful. So in the end, I want to say this defense is not only a milestone for my PhD study, it's also a new starting point of my future research path. I will hold on to the passion and use what I learned to continue to make my contributions in the future. And with that ends my presentation today. Thank you very much. I understand the time might be short, but I'm happy to take any questions and comments.
Hi, Hansi. Thank you for the great presentation. I do have a question.
Yes.
Can you go back to slide page 16?
Page 16.
Yes.
Yes.
Yes. So I see for the contrastive loss, there is a term which is, oh, that's the margin minus. Okay, I see.
Yes, yes, it's a reversed way. So the y equals 0 here means the same. Y equals 1 means different.
Okay, okay.
And
sure.
and the margin minus, yeah.
Mm-hmm. So you here use the cross product. I want to just double check.
Where no, it's just dot product. Are you referring to this
yeah,
multiplication mark?
yeah,
It's just normal multiplication. It's not cross product.
Okay. Okay, sure. Okay, that's cool for me. Thank you very much. Yeah.
No problem.
Yeah.
I have another question. In slide 28.
28?
Yes, and also in 29, where you present the results.
Mm-hmm.
Yeah. So how you can tell that there is a difference?
So
whether the theory that you used to do the comparison to.
You're asking about the difference, or
yes? How can you tell that these bars are different from each other?
Well, so if you look at the colors specifically, different colors represent different ablation study when we use different part of the wireless data to train the network. Clearly, the yellow bars are always higher, and that means the accuracy is higher, right? And
no, but my question is, if you run a typical statistical analysis, you would find probably that statistically they are not significantly different. So I wanted to know, you run in a statistical analysis, or it was just a study by eye, by looking at the means?
Wait, I'm not sure I'm following your question. You're saying if I run statistic analysis on this data, or I will not find any differences? Is that what you're trying to say?
Yeah, I'm asking if you run it or you did not.
So I'm not sure. First, I'm not sure what do you mean by statistical analysis. Here we test the accuracy. We compute the accuracy using the total number of correctly associated bounding boxes divided by the number of total number of bounding boxes in an image frame, and that is how we compute our accuracy for every frame, and that's how we compute these bars and its deviations for all the test set, and we compare it for if you take a look at the yellow bar, this is our method when we do not use the voting scheme, and for indoor environments, when we use the voting scheme, we do observe that there is no significant difference with only marginal increase. But for outdoor, oh, this, by the way, I'm sorry. This is the comparison between the bipartite association and our affinity matrix learning. And in terms of difference, you can see clearly that for outdoor situation, our deep learning method exceeds the bipartite association by a great margin. Is that the difference you're trying to looking for, or you're referring to something different?
Yes, but so for if you go to like 39.
39.
Yeah, you present the results.
Okay.
Yeah, so here too. So did you run a test here, a statistical test, because the variance are so big, are so large, that I am sure that you will not find any significant difference between these three methods. So I was wondering, how is the norm to compare the three methods here? What is the techniques that you use to compare them?
So, okay, when we test the network, we can compute the localization error for every person at every frame, right? And because we have 5 test sequences, each 3-minute video, we can have a lot of localization error numbers. And we simply gather these numbers and we can compute the numbers of mean, these numbers, standard deviation, the median of these numbers, and 95th percentile. So these critical points on this statistical curve, if you plot a CDF, cumulative, the probability of cumulative density, then that CDF is more like a smooth or a connected dots of these critical points. But here, in terms of clarity and more direct comparison, we just list these critical numbers here. And in comparison, this box plot also shows critical statistics of these numbers. So the box plot, the yellow line here represents the median, and the green line here is the average, and the box itself is the 25th percentile and 75th percentile, and the two edges are the maximum and minimum. Does that answer your question?
Yeah, no, this is clear, but it's okay, thank you. No, I just thought that you run a statistical test because all the percentiles are intercepting. So I just was thinking from a data science point of view, these wouldn't, I mean, because all the box plots are intersecting with each other, it would tell you that you don't have any significantly different, but I just wanted to know that. Thank you.
I'm still not convincing why you believe that there's no significant difference.
Oh, because if you run a test, you can know. If you run a statistical test, if you didn't, then you cannot know.
Oh, okay.
Yeah. I just wanted to know you did a test. Yeah.
Okay.
So Hansi, I had a general question here. These results move you closer to meter level accuracy. Is that the type of range that is required for pedestrian safety? Has anybody worked on the application layer on top of this, which will know that there's some degree of inaccuracy? The other things that are being done at application level to deal with that?
So this project was for a novel application for pedestrian safety in a smart intersection. So we would want the level of accuracy to be as high as possible. If we can achieve like 1.5 meter error for every intersection, especially for those intersections with original noisy GPS measurement, then it would be great for other vehicles or other traffic participants to know that there will be a pedestrian somewhere, and this information can be transmitted from the roadside unit side to other traffic participants like vehicles or other pedestrian smartphones, so that it can create more interesting applications for traffic safety. For example, a vehicle's camera is facing some other way, so some of the pedestrians' location the camera is not seeing, but with the roadside unit's help, it can infer that person's location with respect to the camera, and this data can be transmitted to the vehicle. So after correct coordinate transformation, the vehicle will understand that at some place in this intersection there is a pedestrian, and that place is not drivable.
Right. So I agree, these are quite interesting applications that will become feasible. My question was, what do you think is the right amount of how many meters accuracy do we need to make these applications worth having? Or is a false positive problem could be quite severe?
In terms of the level, I think because a human is more like less than a meter's width, right? And the stride of each person is about 1 meter every second. So I think if we can achieve meter level accuracy for these pedestrians, then we can be a little bit more conservative and let the vehicle know that probably at that place and within a radius of 1 meter, that there's a person, and I think that would be good enough for this type of application.
Okay, thanks.
Thank you.
Now, I feel this is a very interesting work, especially you connect the vision and the Wi-Fi together. So I think that this very interesting exploration. So my question related to that, like for the when you do the localization, and you have vision camera information and also the Wi-Fi information, right?
Right.
Like how do you know that, okay, when the other modality needs to be kicked in, like during the real time, and how frequently you need to, switch between these two modalities, or you're always going to look into the data from these two different modalities?
So in terms of practical usage, when we train the network, we would use data from both modalities. That means I can imagine a situation that probably after days of recording, we come back to the lab and then we gather the whole day's data, and then we choose the moment where probably during the night, probably in some less busy hours when there's only 1 or 2 person around, where we can easily figure out the correspondences. We will collect those data and use that data as correspondences to train the network. And after that, except that, when the network is deployed and in inference, it only requires users' phone data. It does not require the user's camera data to kick in to make inference. But that being said, the camera still records everything, right? So it's like and during the day, the camera is recording and make inferences for pedestrians' location, and also the pedestrians' generated location can be associated with the camera's coordinate. And then after some time, probably a week, probably a day, as a cycle, we can generate more data, accumulate this data, and then at some time we retrain the network. So the next time the network makes inference on person's phone data, it will make more accurate locations. And then this location can again help the existing camera data to associate to each other. And then the data can be expanded again and again.
Okay. So this system is always on.
Should be.
Okay.
Should be. So
Okay.
yes,
So do you
I
have
guess
an-
you're asking about the feasibility. How do we use it in real world? My thinking is that we first need to initially train the network, and probably at that initially training stage, the system is off. And after the initial training is done, we can deploy the network at that place and then make it work for everyone. Although at the very beginning, the produced location might not be that accurate, but as time goes by, when we accumulate more and more data using the self-learning approach, the performance will gradually converge to some numbers. But unfortunately, I haven't made that evaluation here.
Okay, thank you.
Thanks.
So a couple of comments or questions. Hansi, can you go back to slide 9? And can you tell me what's your intuition about why appearance is doing better than depth here?
Slides number 9. Is this the slide talking about?
Oh, gee, no.
What?
Maybe.
So could you repeat your question?
Yeah, so the question was, can you comment, give your intuition of why appearance is doing better than depth? Must have copied down the wrong slide number.
I guess
Maybe it was
probably
19.
this is the slide where I list all the possible choices to compute edge scores. And why appearance is better than depth is because in reality, let's say in an ideal situation where there's no measurement error and no GPS error, suppose we have a location, suppose we have a measured location of a certain vehicle somewhere besides us. If that location is 100% accurate, then we would simply compare the two observed location. That's enough for us to know whether the two vehicles are the same or not. But in reality is when we measure the vehicle's depth and when we compute this depth score, we need to convert the depth into the same coordinate system frame. And here in our implementation, we compare the two observing vehicles' GPS, and we subtract that GPS difference into the depth spatial score. So in other words, this depth score is no longer 100% accurate. It contains errors. So sometimes we might see a situation where two vehicles' depth are quite close to each other, but they're actually different because of the measurement error. So that's when we would need other reference like color, like appearance information.
So it's your appearance matching. Okay, my next question is on slide 25.
This is it. Is this a slide?
Yes. So your dimensionality reduction. So at that in this portion, you have a lot of options for dimensionality reduction. And you've done so with layers that are effectively doing some filtering and downsampling. Can you comment on what other options might go there?
I haven't really thought about other options to reduce the size of this cubic. The reason is because when we look at this cubic from the right side to the left side, each concatenated bars actually represents a potential association decision for a specific phone and a specific bounding box. So we would only need a splice of this cubic, of the intersect of this cubic. So that is why my first option goes to fully convolutional layers, because it is directly doing what I wanted to do. We use a filter bank to look at the whole the depth of this concatenated feature vectors, and then squash this 64-dimensional width into one-dimensional, and only leave one number behind. In other words, it's more like we're using a fully connected layer for every connected feature vectors, and we're using a fully connected layer to convert every connected vectors from 64-dimensional to one-dimensional. But using a fully convolutional layer allows us to reduce the dimension. It's more like a fully connected layer in another dimension, in a horizontal way. So that's why I was going with this direction.
Mm-hmm.
Yes, thank you, Hansi, for this wonderful presentation. I personally have a hard stop at 2 p.m. and I'd like to reserve a little bit of time for a closed session. But we also have our outside committee member Hongsheng here, so I wanted to give Hongsheng at least one opportunity to ask Hansi a question.
Yeah, thank you, Marco. Great presentation, Hansi. I do have two questions. Can you please go back to page 18? This is sort of related to Dr. Dana's question about the importance of different features. So I understand the primary reason behind using a combination of different features is you want to explore, achieve a better performance. I wonder if you did any appellation study to understand what's the importance of position-related features versus visual-related features in improving your performance.
So this result on the left, I think it serves as a more like an appellation study, right? It compares. So this is when we use different types of features, and we want to make predictions for every pairs of Curie images, whether they're the same or not. When we only use depth information, just like I said, it could be unreliable. So that's why we're observing a nearly 50% area under curve. That's almost half of the square, as you can see, because sometimes a very close distance or very similar depth measurement actually comes from two vehicles, but that two vehicles just have noisy measurements, so that's why they gives us an illusion that they're at the same place, but they're actually not. But in comparison, when we add more information to that feature vector, suppose we use depth and color histogram together, we can see some improvement. And if we use more data, more dimension of feature points like sift to serve, we have some other improvement. And then if we move on to the deep learning features that are trained using our network, this is how we really see some satisfactory results, because the curve now is leaning towards the top left corner. So I think this layer by layer comparison serves as an ablation study where we first just use depth, and then we use depth with color histogram, and then depth color histogram with some more advanced features, and then finally appearance or kinematic. I would say that now I wish to add some more combinations, because there can be many. There's depth with appearance or depth with, you can play around with this combinations of features, but I think this would be some typical configurations that we can draw some conclusions, and it seems a fair like ascending in terms of complexity and features it's like an advancement of the complexity of the feature vectors.
So just to clarify, the last curve is labeled appearance plus kinematic. For that case, did you use any depth information?
Yes, for this,
okay.
for the last curve, here is the configuration of how I trained the network.
Okay.
So we basically add the depth score and find a way to append that depth score into the feature vectors derived from appearance. So that's why I call it appearance with kinematic, because this feature, once it's concatenated, FU append by SU, FU is coming from appearance and SU is coming from spatial and depth information. And after that, we render it using a fully connected layer so that a new feature vector is constructed. So that's why I call it appearance plus kinematic.
Right. So if I compare the last two curves, it suggests that the contribution from GPS and depth is limited, if I understand the correctly.
Yes. In this case,
so,
yes.
Yeah. So that actually brings me to a more general question.
Would it be okay to take that question offline to give us a chance to sort of think about Hansi briefly?
Okay.
Or do you feel that this is a question that sort of needs to be answered right now?
No, I think we can take this offline.
Thank you so much.